Hello, today I'm going to go over how to design a hyperrocket engine, but this is kind of your short high-level talk that just walks you through the steps without giving you everything that you need to come to a fully designed engine. So the way I see engine design flow, I divide it into 6 different steps. And while a hyperrocket engine is difficult to design in some way, it's easier in the sense that you can determine a lot of your working variables with very few simple equations. And those are the equations that you see in front of you. So, okay, let's go step by step. There are 6 big steps. The first step is that, well, you first want to kind of understand your system. And when I say understand your system, you want to know what is the mass flow you're dealing with. So here we see the equation ISP is equal to F over m dot g. That is your typical equation to determine ISP after a test, but it is also used heavily to get your initial engine dimensions. So here you would just simply rearrange for m dot, and remember m dot here is the sum of your oxidizer mass flow rate and your fuel mass flow rate. So you would rearrange for m dot, and then you would plug in F as your desired thrust, and then you would plug in ISP, which is typically your optimal OF ratio, given your propellant combination, unless there is some sort of heat considerations that you're dealing with. And then G is simply a constant. After that, you solve for your m dot. And then following that, using that optimal OF ratio that you have obtained from NASA's CA run, you would then use that to calculate your oxidizer mass flow rate and your fuel mass flow rate individually. So that's gonna help you understand, okay, does your fuel grain currently provide enough regression rate, and and allow you to design your feed system with that initial m dot O, which is not subject to change drastically, even when you use some sort of relation to determine the chamber length in the future. And then following that, you want to solve for your nozzle dimensions, and you can do that using your typical thrust coefficient equation. So here you want to rearrange for AT, which is your throat area. So AT would be equal to F over PCCF. So CF is another value that you would determine at your operating OF condition, and you can do that using NASA CA run. F again is your desired thrust, and PC now is your desired chamber pressure. So looking at this, of course, holding thrust constant, the driving factor for a chamber pressure would be throat area, because CF does not change drastically. It's around maybe it could be like 1.2 to 1.8, whereas throat area can affect your chamber pressure a lot more. So just remember that here, your throat area is always your driving factor for chamber pressure. And then now you have your throat area, right? But you need to find your nozzle exit area. You can do that using expansion ratio from NASA CA run. And then now this is where the more complicated part is, so this will be covered in a separate video. But then you want to determine the chamber length based on your required regression rate, right? Remember, we don't have a direct control over regression rate, and regression rate is how fast the fuel recedes over time, in which you can think of it as kind of like how much mass flow rate am I receiving from the engine at any second. And because we're working with the hybrid, we deal with the downside that regression rate, how fast our fuel burns, or you can think of kind of like m.f, depends on the length of the fuel grain. So we have to size that carefully in order to actually achieve the OF ratio that we have set for our engine. Following that, you want to decide on your injector. Shorter engines, you might prefer ones like swirling injector. For longer engines, you want to go for shower heads. You finalize your chamber dimensions. So previous step, you would have determined the length, and then you finalize your nozzle, taking some engine design considerations like where you're gonna put your pressure transducers, do you need any liners, things like that, and you should be good to go.